Hello everyone, we are going to be working on some applications of differential equations. We're going to be looking at concentration and a mixing equation. So first off, let's make strong coffee because we're going to get ready for a night of study. And when we pour 200 centimeters cubed of boiling water into our mug, then we go ahead and put 10 grams of coffee in and we stir it up, mix it all together. So from that, what is the concentration of the coffee solution in grams per mils? So concentration is given by mass divided by volume. And the mass of the coffee we added was 10 grams for a volume of 20 cubic centimeters. Now an important thing is that 1 cubic centimeter is actually the same in size as 1 milliliter. So we can express the units there as grams per milliliter. And we get 1/20th. Okay, not too bad. That's a good start. So let's remember this. We're going to draw on this in the next questions. So now we realize as we're drinking the coffee is too strong. And so we better go add a little bit more boiling water, and we're going to pour our water into our coffee at a rate of 10 mils per second. And of course we're going to stir it up to make sure it's continuously mixing. However, we've chosen the dodgy cup, and a crack develops in the base of the mug, and the coffee solution leaks out at a rate of 2 mils per second. Alright, so there's our little cup with our coffee. Charming. And we're going to pour in some more water. However, oh dear, there's our crack and it's leaking out. We've got 10 mils per second pouring in, but it's leaking out at 2 mils per second. Okay, so that's our flow rate. And it's good to illustrate our problem with a little diagram like that, just so you can visually see the flow rate in and the flow rate out, so they can help us to form our differential equation. Alright, part B says, if X is the amount of coffee powder in the mug after T seconds, show that the differential equation related to X and T is given by this equation. Nice one. Okay, let's have a go. So, first off, from part A, okay, we had remembered that the water in the cup initially was 200 mils, and we added 10 grams of the mass of our coffee powder. Okay, so we're going to draw on that as the initial condition of our differential equation. So the basic structure of the differential equation starts with, here we go, the rate of the mass with respect to time is given by, this is the flow rate in of mass, and this is the flow rate out of mass in the solution, and so we want the net flow by doing the subtraction. So this related rate via a differentiation chain rule is our mass with respect to volume, so that there is a concentration rate of change, that's our concentration derivative, and this is volume with respect to time, so that's the flow, the water flow derivative, and so on. And that's our related rate for into the solution of coffee, and this is the related rate of change out of through the crack. Okay, so let's now bring ourselves back to information. It says here we add more boiling water at a constant rate of 10 mils per second. So it just mentions that we're just adding water. It's nothing about we're adding a mixture of water and coffee. So there's no solid coffee has been dissolved into the water. So no coffee, that means there's no concentration, zero concentration added into the coffee mug. So it makes this term here. That makes that one there, that becomes a 0 term. Now, the next thing, here we go. When we think about the flow going into the coffee cup and the flow coming out of the coffee cup, we're going to have a volume of the coffee in the cup that's going to change with time, and so we've got to identify the net rate of change of volume, the net flow, and integrate to get a function, a rule for volume with respect to time. So the net flow is the flow rate in minus the flow rate out. And from our information, the flow rate in is 10 mils per second, the flow rate out is 2 mils per second, so overall we've got a net flow of 8 mils per second. So we use that and we integrate that constant to get a 8 times t for time plus c, our integration constant. So when t equals 0, our volume was 200 mils, so that makes our integration constant at 200. And we get our rule down here, volume equals 8t plus 200. So let's include that in our DE. This term here is a 0 term, so we don't have to worry about that. So all that's left is the second term, and we've got the solid x divided by the volume at a point in time, so there's our volume amount, 200 plus 8t, multiplied by the flow rate out of the cup, which was 2 from here, 2 mils per second flow rate out. And finally, this factor of 2 cancels out a common factor of 2 in your denominator, so it becomes 100 plus 4t in the denominator, and we can just add that term onto the left hand side and we get that, which is the same as what we're after, and we did it. Okay, so that's our work to set up our differential equation. Now let's go about solving our differential equation. Solve the DE and express x in the form of, okay, so we've got this, as you can see, we've got this exponential term with a reciprocal linear function on time. Now, so let's start with our differential equation from the previous question, and let's rearrange. I'm going to subtract it back to the right hand side, and now I'm going to separate my variables. So I'm going to divide by x on both sides and multiply by dt to the right hand side. So I've separated, there's all my x terms, there's all my t terms, and let's integrate on both sides. We are going to get the natural log of modulus x is equal to, and here's this, our integral of this 1 over linear, the gradient of the linear part comes out the front, times log of the linear function itself. Don't forget the modulus, and don't forget the plus c, the integration constant. Now let's use our initial condition. Now from part A, initially the concentration was 10 grams out of 200 mils. So our amount of mass that was added was 10 grams when at the starting point in time. So doing that substitution, we get this expression for which we can solve for our integration constant c, and tidying it up a little bit, we get the natural log of 10 times root 10. Okay, let's now bring that back into our equation. There it is. And just by recognizing that, the t pronumeral is representing time, which is always positive, greater than 0, and the x is representing the mass of the solute into the coffee, which is the coffee, which is also a positive value, and so that way we get to drop the modulus, because inside the brackets of the log it's always going to be positive overall. So we can drop the modulus sign. Okay, now one little thing here we can do to start to manipulate it so we can bring our logs together. I'm going to multiply both sides by -4, so that removes the fraction. But it puts a -4 here on the log on the left, and this term, don't forget, distributing the -4 to this term over here as well. Okay, so what we end up here, now use our log law, raise the 4 to become the power of the 10 root 10, and the subtraction of logs brings a fraction together inside a single log bracket. And see this big number, this 1 million? Well, that 1 million there is the result of 10 times root 10 all to the power of 4. Now we have also this part over here, this -4 can become the power of x, so we get an expression having over here a 1 over x to the power of 4, and that there should be a positive power of 4. That's better. Very good. So transposing 4x, we have to now get the reciprocal of this right hand side and then do the 4th root, and we achieve this as our function of x. And if you look closely in the question, that follows that same form that we have here. So we did it. Okay, what's the next bit? Well, how long will it take for the mug to overflow? Well, to work that out, we have to have an idea about the volume of the mug. How big is the mug? Because if we're filling it with water, then we need to know the size of the mug so we can work out when it's going to overflow. But then the problem is we didn't do that previously, and we don't have that question available to us. So we need to know that volume of the mug, which we don't. But let's express it like this. Let's say that our volume max, we're going to say that's our maximum volume of the cup itself. And so the volume of the coffee at any point in time overflows when it's greater than the maximum volume. Okay, so we'll set up an equation like this, and we go ahead at solving. 200 plus 8t must be greater than the maximum volume, and when we solve for time, you would get a little equation like this. So time being more than this amount, that's when the mug would overflow. Alright, not a problem. Let's look at the next part. Determine the time it takes for the concentration of coffee in the mug to be halved. Correct to the nearest second. Okay, so concentration. Concentration again is mass divided by volume. So we know the mass of the coffee in the cup, that is x as a function of t, and we know the volume of the boiling water in the cup as well. That's V as a function of t. So the concentration of the coffee must be the division of those two functions. And we use both functions and we set up this overall concentration function. And initially the concentration of the coffee is 1/20th, and we did that from part A. That was our initial concentration. So how long for that concentration in the mug to be halved? So what's half of 1/20th? It's 1/40th. So we grab our overall concentration function and we equate it to 1/40th, and we go ahead and solve for time. So that's definitely, look at the type of equation you have, that's definitely a CAS exercise. So let's CAS it. There it is. We set up the equation in the CAS like so, use our solve function, and we can get an exact value for time. And we want our answer correct to the nearest second, so we approximate it and we get 18.527. To the nearest second it must be 19 seconds. There we go. Happy. Thanks for watching.